Hello, I guess. Okay. Okay, good day. I'm Winston Baring and I am going to present my elemental. Since I were able to solve this in my previous exam, I would be explaining my code here. So the first thing is that I have just make a elements as well as alloys here because alloys is another type of element that has two elements. And then in my element, I have this fields, the atomic unit, atomic emblem, which is the symbol, identity, and the pressure, which is the weight, and the boiling point and the melting point. Supposedly, I would going to put that one here in my subclasses, but I have decided to put it in the element and then use it whenever they have a specific kind of fields like this. So we also have a state here, which will return if it is solid, liquid, and gas, and we have used that one here. If the temperature is greater, is less than, then it will return 1. If 0, it will return, if temperature is less than, greater than the boiling point and the melting point, then return 0, else will return 1. And this is our constructor. We have our weight comparator so that we will be able to compare any number. This is just basically comparing the numbers. So even though this is a weight comparator, it will just compare the numbers. And we also have our getters and setters here. And since it was asked to implement the anti-SID here, which has the following constructor, and it has a half-life which will return, which has a initial value of 0, and then that half-life, we also have the radiate that will return our atomic unit and the symbol, as well as it will imitate radiation, and it will also return our life, which will be counted half-life here, half-life. So for our uranium, we will be extending antacid since we'll be using its superclass here, and then we have this new subclass which is a uranium, which has a half-life of 25166, and then we'll just be returning its half-life and imitating radiation from its radiate radiate effect. And for our transition metal, we have extended it to in the element, and then we have just extended it. First, we have our constructor. We'll be using this one to get the superstring of our subclasses. One example is this, the gold. We have used our subclass here. Super constructor, so that we will be able to input this element unit, symbol, and then the name, and the weight, boiling point, and melting point, and the boiling point here. And since the transition metal gold extends to transition metal, which inherit from our extend element, they just have the same base class, and implements conductive, which is the percent conductive. I'm sorry for my... Okay. Maybe I should close my Grammarly. And we also have the conductivity, which will return the atomic unit, the number, and the element emblem, which is this is the weight, and the percent conductive, which will just be multiplying. Since we have a percent conductive of 0.7, that means we will be multiplying that by 100%, so that it would be 70%. So for the zinc, also we have our class titanium here, just a basic implementation of the per class, and then return titanium, which is this kind of function, implementation. We have our zinc, which has a percentage, and then we have just used the same print method. Because this has a return type of void, we'll just basically print the atomic unit, this, and this. And we also have our iron, just the same, which has a super method magnetize. The difference in the iron is that it has a magnetic interface, which will return, which this one will return 1710, and the it also have a magnetic type, which is a ferromagnetic, the iron. And for our copper, we have just used transition metal extend and conductive. We have our string here, our constructor, percentage conductive since this one, and we'll be returning the print method of this conductivity. We will just multiply this by 100, this return value of the percent conductive. Just the same case with our technetium, which has a cognitive, magnetic, and radioactive properties. First is that the constructor here, then the percent conductive. We'll also be printing our percent conductive over here, and the magnetize, which will return our magnetic type and magnetic strength here, this one, magnetic type and the magnetic strength. Also the emblem, which is the weight, the symbol. The half-life of 61, since technetium has a half-life of type Techni 1, 61, and then we'll just be returning that one in our radiate, which will imitate a radiation and then return the half-life. And also in our magnetic string, it will return 270, and then our magnetic type is paramagnetic. It will return, this one will return here. And our here, the magnetic. Where's the magnetic? Here, magnetize. It will return the magnetic type and the magnetic strength. So for our post metal, it will just also same. It will extend from the element. It has a constructor, and we have extended our class. We have created another subclass, which is the tin and the aluminum. In our tin, it's just basically we have just used the super method, and in our aluminum, we just have implement conductive, since it is conductive and it has a percent conductive, and then we will just basically print this one. This is for our input, by the way, and we have our conductivity, interfaces here, which is the conductive, magnetic, radioactive, and those are those have a field and a class of conductivity. This is not a field. This is a method. Abstract method, abstract method, abstract method, abstract method, abstract method, and abstract methods. And for our alloy, this is a different type of element. It's like we have used another element here, and they are just basically this another list. This is another list. So our public alloy has the component 1, which is the element 1 and 2, and it also has a identity. So the first thing we have just set here, the super method, the constructor, and we have extended, we have make a subclass, which is steel, bronze, and brass, and a few getter classes. Getter and get identify, which will return the identity. So here in our steel, we have implement magnetic. We have just extended that one in our iron, and we use the super class, and then we have override the magnetic strength, magnetic type, and we will be printing that one. And as well as to our bronze, since we don't have any interfaces that we'll be able to connect this one, we have just simply connect this, use the superclass method to connect it to the alloy. And after that one, to our brass, we have extended our brass to our alloy, just the same, and implemented the conductivity. Simply, we have our constructor here, and then the conductivity is, our percent conductivity will return 0.28, and then we'll be printing that one using this method here. That's it. And for the main, whenever they print, it is a dual loop. It is already implemented, but here whenever someone type copper, gold, or any other elements or alloy here, it will just be added in our list. So if element is added, then it will be added to our list new transitional.copper, and if an alloy has been added, then it will return to our alloy.list here that it is a alloy, and it will be added to our alloy. So after that one, we'll be choosing an action after we added our element, all our elements and iron, and whenever we are done, we type done, it will finish the case, and then enter the next action. What action would you like to do with your element and your alloy? So the action that we have is the radiate, magnetize, conduct, and alloy components, get state, and sort by weight. This is our weight comparator, the get state, alloy components, and yeah, all of the other parts. So first here is that our radiate, we just have a counter here. This is a counter, and then we will be traversing in our counter, in our list, and then every time we traverse, we will be adding 1, and then if that will be more than 0, then if that equal be to 0, then no radioactive materials are present, which means we don't have any radioactive materials. Else we will be printing our radioactive material, which will print radiate, and yes, this radiate over here, conductive radioactive here, which will print this one. And after the radiate, we also have the magnetize. This is just a counter, and every time it will be called, every instance of the element, then it will be printing the magnetize void method. And since magnetize was for the element and for the alloy, we have our traversion method both in our element and in our alloy, in just the same case. And if any of those is equal to 0, then we'll be printing no magnetic materials are present. And for the conductivity, just the same case. We have, since conduct, we have conduct in our element and in our alloy. We'll just be having a counter method, and every time that it equates to 0, there is no conductive material. Else it will be printed all the conductive materials. So for the next one, which is the alloy components, this is the components of the alloy. We have just a counter here, and we will just traverse into our alloy of list, and then we'll be printing the get identity, which is the identity of our alloy, which will print the one here, alloy, which is the alloy. This one, identity consists of component 1 and the component 2. So the two elements that will be print, what elements are composed of our alloy. And then rat, if that does not equal to any number, it will be equal to 0, then no alloys are present. So in our gate state, it will just basically return the state if it is solid, liquid, or gas. And we will be entering the temperature, and then we will be comparing the one to our, we're storing that one, and we'll be getting that one in our get state, so that we will be able to compare here, which is the get state, this one. Not this one. The get state. Here. This is the implementation. If the temperature is smaller, then it will return 1. If higher, return 0, -1. If greater than the melting point and boiling point, so it will return 0. So that's for the implementation of our get state. And if it return to 1, it will become solid. If the get state temperature were equal to 0, it will become liquid and a gas, and else it will become a gas. And we have just traversed our element here. So for our sort weight, we have just sort that one first with our sort comparator, as what I have shown a while ago. Then we have just traversed in our elements, and after traversing, we will be printing each of the elements based on the weight. And then if the elements is empty, then there is no elements present. And then if after all those things, if you will input done, it will be done. That's it. I am Winson Baring, BSc History under J. Vince Salato. under ay F3. Winson Sibaring F3, BSCS2 under Sir J. Vince Rat.